Hey guys, welcome back to chapter 10. Today we are going to introduce this idea of something called simple gas laws. Before we can dive into the simple gas laws, we first need to talk about the properties of gas that we're going to study. So there are four basic properties of gases that we're going to study. Those properties are pressure, volume, temperature, and then the amount of gas. So when we talk about pressure for these gas laws, we're typically going to be talking about the units of ATM. Very often your textbook will mix in some millimeters of mercury, but for the most part, ATM is going to be the unit that we deal with. We can also talk about the volume of a gas. So how much volume is that particular gas taking up? Is that increasing or decreasing? So when we talk about volume, the unit that we're going to use is the unit liters. So nothing really new there. Temperature. So we can talk about the temperature of a gas. Do we heat it up? Do we cool it down? For the temperature of a gas, this is going to be really, really important. I'm probably going to say this 100 times in this chapter, and it's still going to trip somebody up on the exam. So when we talk about temperature for this chapter, it has to be in Kelvin. So the temperature units absolutely must be in Kelvin. And then when we talk about the amount of a gas, so we're at the end of the semester here, we're all chemists, right? So when we talk about amount in chemistry, we talk about that in the unit of moles. So that'll be the unit we use. All of these properties of a gas sample are interrelated. So when one changes, it affects all of the other properties. So what we're going to look at first is we're going to isolate these properties. So we're going to look at the interrelationship between two properties while we hold the other two constant. So we may look at pressure and volume and how those are related to one another. But if we're looking specifically at pressure and volume, that must mean the temperature staying the same and the amount of gas that we have stays the same. And that's a pretty easy scenario to set up. It's done in a big open room. The temperature is probably going to remain constant. And if it's a closed system, then we can make sure that none of the gas escapes or we don't add any to it. So it's a pretty easy scenario to set up. So let's dive into our first simple gas law. In our first simple gas law, we're going to be looking at Boyles Law. So that's going to be the pressure and the volume. There'll be two more videos that come out after this one. One of the videos will be for Charles' Law, and the other video will be for Avogadro's Law. But these are going to be the three simple gas laws that we talk about. So let's dive into Boyles Law. So Boyle's Law is going to investigate, like I said, the pressure and the volume, which means temperature and amount are staying constant. So to think about pressure and volume, one of the easiest examples to think about is a tire pump or a basketball pump. So I'm going to give some terminology just so you guys understand what it is I'm talking about as I set up this example. So in this tire pump, we've got this open area here where the air exists. I'm going to call that open area the cylinder. So inside of this tube, we're going to call that the cylinder. And then the handle that you pull up and push down, we're going to call that the piston, just so we're on the same page when I talk about different parts of this. So this thing that goes up and down is going to be the piston. So the first thing we're going to talk about is the upstroke. So if the piston is all the way down here in the bottom, and then the change that we're going to undergo is pulling that piston up to the top. So if I pull that piston all the way up to the top, what is going to happen to the volume inside of that cylinder? So the volume was just this little area here. I pull the piston up. Now the volume is this whole big area here. So pull the piston up, volume is going to increase. Boyle's Law is going to look at the relationship between pressure and volume. So if the volume increases, what's going to happen to the pressure? Well, pressure is going to decrease. Okay. How do I know? Don't take my word for it. How do I know? So how I know this, what I'm going to observe is as I increase the volume, now the pressure inside of this cylinder is going to be lower than the pressure on the outside. So when I pull up on that piston, we're going to hear air rush into the cylinder, right? Low pressure inside, high pressure outside. The gas is going to say, hey, I want to go where there's lower pressure. So we're going to see gas go into that cylinder. So let's talk about the opposite scenario over here. So to start, the piston was way up here, and now I'm going to push this piston down to the bottom. So what happens to volume? Well, it used to be this big old area. Now it's that teeny tiny area. So the volume is going to decrease. If we decrease the volume, what's going to happen to the pressure inside of that cylinder? The pressure is going to increase. Well, how do I know? What do I observe? Now, the pressure inside of this little area right here is really high. The pressure on the outside is really low. So that gas is going to say, wow, I'm under way too much pressure here. And it's going to leave this tube. And it's going to rush into your bike tire. It's going to rush into your basketball, whatever it is that you're trying to fill up with air. So that's the relationship between volume and pressure of a gas. And remember, we're keeping temperature and the number of moles constant. So here's the official definition of Boyle's Law. The volume of a gas and its pressure are inversely proportional. So here's the mathematic representation of that. This little fishy symbol right here, that fishy symbol means proportional to. And then 1 over pressure. This is how we mathematically talk about inverses. So if I want to take the inverse of a number, I take 1 over that number. So what this symbol represents is exactly what we read up here. The volume is proportional to the inverse of pressure. So let me break that down. What does that even mean? What it means is when one goes up, the other goes down. When one goes down, the other goes up. So they move in opposite directions of one another. For each of these examples, we're going to kind of refer back to or lean back to the kinetic theory. So we are chemists. We probably aren't talking about blowing up tires or basketballs. So we want to know, well, why is this the case? What do I know about the particles? If I look at the particles, what's going on here? So as a volume decreases, that container would become more crowded. So if there's less space, more crowded, there's going to be more collisions with the side of that container. And that means more collisions means we're going to register a higher pressure. The opposite is true. If I pull that piston to the top, now the volume increases. There's more room to move around. We're going to have less collisions with the side of that container, which means we're going to register a lower pressure. So if you guys have ever been certified for scuba diving, you've actually learned Boyle's Law. They just didn't tell you it was called Boyle's Law. So what's one of the rules of Boyle's Law? What's one of the rules of scuba diving? Well, when you're down deep in the water, what you do not want to do is hold your breath and swim to the top as fast as you can. Why not? Well, when you're down here, let's say 20 meters deep, your body, and specifically your lungs, are feeling 3 atmospheres of pressure. So the pressure is higher down there. If you were to hold your breath and swim to the top as fast as you can, the pressure would change from 3 atm to 1 atm. So by doing this, pressure is going to go down. Well, if pressure goes down, what's going to happen to the volume inside of your lungs? Yeah, volume increases. So if you were to hold your breath and swim to the top as fast as you could, what's going to happen to your lungs? Somebody always says they're going to explode. Probably not going to explode, but certainly that volume is going to increase inside of your lungs. Most likely it's going to force you to breathe air out, but certainly something very dangerous. There's also other side effects other than just Boyle's Law of doing this, but this is certainly one of the things you have to think about. So just another example of Boyle's Law. So now what we're going to talk about is how are we going to math with these simple gas laws. So what we're going to look at with these simple gas laws is we're going to look at two different scenarios. We're going to talk about what was the situation or scenario at some initial time, and then what was the situation or scenario at some final time. So for example, if we're looking at this diver, initial conditions would be down here. So pressure would be 3 atm, volume might be 2 liters. And then we say, well, he swims to the top up to 1 atm. Well, now what's the volume up there? So we're going to look at some initial time, some final time, and see how these numbers are interrelated. The formula that we're going to use to do this is the following formula. So P1 V1 equals P2 V2. So P1 and V1 are going to be the pressure and the volume at some initial time. So the beginning before we do a change. And P2 and V2 are going to be the pressure and volume at some final time. So after the diver swims to the top, for example. So then we're going to have 3 of these variables and then try to solve for one of the unknown variables. So here's an example of what a Boyle's Law problem might look like. Imagine a diver's gas was initially at 765 millimeters of mercury with a volume of 1.78 liters. What would the pressure be if the diver exhales and the volume is decreased to 1.25 liters? Okay. So for these problems, I'm going to teach you guys how to keep yourself organized. So the math, the algebra of these problems is actually very simple. We just need to make sure that we stay nice and organized. So the first thing that I do is I like to take inventory. What do I know? What am I trying to solve for? So over here, I'm just going to make a little table of the variables I know and the variables I don't know. All right, so reading through the problem again, a diver's gas was initially at 765 millimeters of mercury, so that's a pressure, and a volume of 1.78 liters, so that's going to be the volume. So initially our pressure was 765, and volume was 1.78. What would the pressure be? So probably going to be solving for P2. So what would the pressure be if the diver exhales and the volume was decreased to 1.25 liters? That's going to go down here. Ooh, that's not what I wanted to do. Okay. All right, so I have 3 variables, one unknown, so I can do some simple algebra to solve for that. So now that we've taken inventory of what we know, now it's just a simple plug and chug problem. Plug it into the equation and chug through it. So 765 millimeters of mercury times 1.78 atm. No, liters. That's not ATM at all. Silly Miss Maz. Liters. Equals P2, which is what we're solving for, times 1.25 liters. Okay. Now to solve for P2, what we're going to do is get it by itself. So to get P2 by itself, I'm going to divide by 1.25 liters, so 1.25 on top. 1.25 on bottom, that cancels. Whatever I do to the right side, I also have to do to the left side. So divide by 1.25 liters. Here we can pause and just follow our units. So I've got the unit of liter on top. I've got the unit of liter on bottom. That leaves me with a unit of millimeters of mercury, which is good news because we're solving for pressure, and that's a pressure unit. And now we just need to plug that into our calculator. So I'm going to take 765 times 1.78 divided by 1.25, and I get 1,089, and my unit is millimeters of mercury. Okay. The cool thing about these simple gas laws is you can always check your answer. So if I teach you nothing else this semester, I want to teach you to ask yourself, does that make sense? Okay. So if I come over here to my inventory, I see that the volume decreased. So volume decreased. So looking at the pressure and understanding Boyle's law conceptually, I would expect pressure to increase. So did pressure increase? Yeah, it did. So 1,089 is a bigger number than 765. So does this answer make sense? Well, yeah, absolutely makes sense. I would expect it to go up, and it did go up. So that's it for Boyle's Law. Pretty simple, straightforward. The next couple of videos, we're going to attack the other two simple gas laws. I hope you guys found this helpful.